Welcome back to Math466 Advanced Applied Analysis. So today, lecture 20, we're going to be looking at convergence when we choose a bunch of points uniformly. So the goal is choose x1 to xn uniformly and independently in 0, 1. Describe the neighbor spacings. And the motivation in the background for all of this is we were looking at the fractional parts of n alpha mod 1 or n to the k alpha mod 1. And when we were trying to understand those fractional parts, we had a bunch of points in the unit interval 0, 1, and then we can relabel those points y1, y2, y3, y4 in order and talk about what's the spacings between them. It's completely deterministic. Whatever the spacings are, it's a computation. And if you actually look at the spacings of n alpha mod 1, it turns out you only see 3 values in the neighboring spacings. Absolutely amazing. When you look at n squared alpha, the behavior becomes more interesting. N cubed, n to the 4th, all that's the same, but n alpha is very different. This is a much easier problem. The reason it's an easier problem is it's not deterministic. We can now use the tools from probability to solve this, or at least to attack this. And this is going to become a really good jumping point to studying random matrix theory, to looking at the distribution of eigenvalues of matrices. So you should have all seen calculating eigenvalues, right? How do you guys calculate eigenvalues of matrices? I go to the computer and I type eigenvalues. Yeah. How did you learn in class to compute eigenvalues? Okay, the determinant of A minus lambda I, right? So if you do this in the real world and you're not shot, it's because they didn't realize that that's what you were doing. You should never do this for a large matrix. The stability issues for something like this is terrible. If you have a 10,000 by 10,000 matrix and you're trying to find roots of a polynomial, no. There's much better things you can do. And so there's entire classes devoted to how you do numerical calculations like that. We will probably ignore most of those in this course unless there's great interest, in which case we can definitely look at something like that. But the main thing we're going to try to understand for the next portion of this class is spacings between events. And in some cases, sometimes the stuff we're doing from Fourier analysis will be useful. Sometimes it will be the framework. When we're looking at n to the k alpha, for n alpha, you can definitely see Fourier analysis is going to be useful. Here, this is going to be more probability. So I have my interval 0, 1, and maybe x1, x2, x3, x4, x5, x6. And I can relabel them y1, y2, y3, y4, y5, y6, so that they're in increasing order. And I can look at the spacings, y 1 minus yk. And then we have to worry a little bit, well, I've chosen 6 points, but this only gives me 5 spacings. So sometimes what you do is you add 1 to y1 and move it over here, and you would have 1 plus x2, and this would become 1 plus y1. And then you would have the right number of gaps, and the sum of the gaps would be 1. And so if we do this, the average gap is of size 1 over n. Or, I'm sorry, I guess, let's use a capital N. Is of size 1 over n. So it's often worthwhile to maybe study zk is n times yk. So we're going to inflate them out. And by doing this now, the average gaps between the z's are going to be of size 1. If I just study this problem as I let n get very, very large, essentially all the spacings are going to be very, very small, indistinguishable from 0. You always want to compare things relative to the average. You want to figure out what is the correct units to study your problem. So for a lot of things, if I know that the average scale is 1 over n, I want to say, well, what fraction of 1 over n is my gap? If it's 3 times 1 over n, then it's 3 times the average spacing. That sounds like a pretty good gap. If it's 1/9 times 1 over n, then it's only 1/9 the size of the average gap. They seem very close to each other. So do you expect, as n gets very, very large, to have neighbor spacings very, very small? Of course. They've got to be small, because on average they're 1 over n. It's, do you expect gaps to be small relative to the average spacing? Do you expect gaps to be large relative to the average spacing? This is how you should also look at the difficult problems about the distribution of primes. Twin primes is very, very hard. Why is it hard? The average gap between primes is of size log x. You're now talking about something of size 2 over log x. I'm sorry, it's size 2. And so if you look at the ratio of the gap to the average, 2 over log x is very, very small. All right, so we want to study these gaps. So the question, does the sequence of neighbor gaps, zk plus 1 minus zk, converge to something nice? And so this has now been adjusted so that it should be average spacing 1. One nice thing about adding this wrapped around is that because we're choosing all the points independently, I can just choose any x and look at what is the distribution to the next choice. That should be the same no matter what x I choose. Right? Sure. I want to figure out what's the gap between y4 and y5. What's the gap between y5 and y6? What's the gap between y2 and y3? If you look at the distribution of the gap y3 minus y2, should it be the same as the distribution of y5 minus y4 and the same as y6 minus y5? Do any of these gaps look different than any other? Or because I'm choosing the points uniformly and independently, it doesn't really matter where I start. They're all going to have the same distribution. So without loss of generality, if I want to, I could start at x1 and say, what's the gap from x1 to the first event? If you wanted to make life easy, you could almost even just translate, because we're doing everything mod 1, and have x1 be at 0. So without loss of generality, study gap from x1, set x1 equal to 0. Because if x1 is not 0, just put in another number line below where you start at 0 over here, and then just wrap around. Yes?
Why do we have the 1 plus x2 and the 1 plus y1?
Oh, because what I want to do is I want to have the same number of gaps as the number of points I've chosen. So here I have 6 numbers but only 5 gaps. So I take the smallest number, the one closest to 0, and I add 1 to it. And so that will give me its gap to y6. And so because that one was x2, I'm calling it 1 plus x2. And because this is y1, it's now 1 plus y1. So this gives you one extra gap. We can't look at y1 minus y6, because y1 is smaller than y6. We can look at 1 plus y1. In the limit, is one extra gap going to make much of a difference? So almost surely no. Is it possible that all of my numbers are clustered over here? Yes. Extremely unlikely. But imagine all of my numbers of size like 1 over e to the n squared. They're all very, very close to 0. Then the average gap among them is very, very different. But we're in a situation where we're assuming everything is uniformly and independently chosen on the interval 0, 1. So because of that, adding just one extra gap is not going to really change the gap distribution with probability 1 in the limit. It's just one extra gap. The other thing is saying, really, here's the problem we're doing. We have a unit circle, or maybe if I want this to have length 1, what should the radius be? I think 1 over square root of 2 pi. So now the circumference will just be 1. And if you want, you can identify this point here as both 0 and 1. And now I'm choosing n angles. And if I choose n angles, I can then look at the distances either by the arcs or the angles, whatever. So there really should be an equivalence between looking at something on the boundary of a circle and looking at points on a wrapped interval. And you can see a lot of the Fourier analysis coming into play here, just wrapping around. It's just a question of which is an easier way to view things. But if you look at it as a wrapped circle, any Asimov fans here? Isaac Asimov. No?
I don't know him too. Not that I don't like him, but I just don't know him too well.
Okay, all right. Then I won't go into the use of a circle in Isaac Asimov's Pivotal Foundation series. But a circle has no end. It has no beginning. Where do you start? Where do you end? What's the first point? We often say, oh, let's make a convention right over here. We'll start this as angle 0. But this is why we want to make sure we have n gaps and not n minus 1 gaps. Was there a question? Or?
You're choosing that radius so that the circumference would be 1?
Right. Oh, sorry, you're right. Yes, there's no square root. You're right, there's no square root. Right, and that would give me a radius 1. That's why I try not to do numbers on the board. Okay, so now going back over here, without loss of generality, we're going to study the gap from x1, and we might as well assume that x1 is at the origin. So here's our first event. And now we have to choose n minus 1 other points from 0 to 1. So choose n minus 1 points uniformly and independently. And so the question is, what's the best way to study? Well, what we can do is we can ask, what's the probability that the first choice is maybe between 2 points over here that are very close? So what scale should I be measuring these choices? How far do you expect the next? The average is 1 over n. So I'm going to write this as t over n and t plus delta t over n. And now t is going to be a real number of size 1. And I want to get a distribution as a function of t. So there's a lot of different ways we can calculate things. So I want to calculate the probability that the first event, the next spacing is between t and t plus delta t. So what is the probability the closest is between, or I'll just say is, in the interval t over n, t plus delta t over n. So how would we do this? So we go through the calculation in the book. How many choices do we have for which thing is closest? Because we get to choose x2, x3, x4, x5, all the way up to xn. Does it matter if it's x2 that's closest or x5 that's closest? So how many labels do we have? We have n minus 1. Well, if you want n minus 1, choose 1. What's the probability that that special one is between t over n and t plus delta t over n? Good. This is the number of labels. Probability, the special, is just watching the Lego movie with the kids, is in the interval. And it will be t plus delta t over n minus t over n. I'm just writing it in a very pedantic way to highlight what's going on. And then what's the probability that everything else is outside t plus delta t over n? That the rest is further. What will that be?
N minus 1 choose N minus 2 and then times the area.
Well, no, it's not n1 minus n minus 2. It's n minus 2 choose n minus 2. Everything else. And what's the probability that each one of them is at least t plus delta t over n away?
1 minus 2.
1 minus
T plus delta T.
t plus delta t over n. And then how many of these do we have?
You do that to the N minus 2.
To the n minus 2. Okay. Do we all agree on this formula? I have n minus 1 choices for the label of the special. If I'm in that small subinterval, this is the probability that the special is in the subinterval. And then because it's the closest one, everything else has to be further away. Does everyone agree with this formula, or is this formula subtly wrong?
It feels slightly wrong that we care about the label of the special.
The label of the special is important. Because otherwise, what you can do is say, what's the probability that x2 is in this interval and everything else is further away? Then add the probability that x3 is in that interval and everything else is further away. Then x4 is in that interval. And so the label does matter. If we didn't include this factor of n, we would not get the right answer in the limit. Yes?
Could we have a problem that there could be 2 points within there?
Yes. And this is the difficulty. If the first point, imagine one point is here, and then we have 3 other points in there. Is that a problem? It's not counted in this case. Now, what's the probability that we had multiple points in this interval? The probability of being in this interval is delta t over n. So if you were to have 2 points in it, it would be on the order of delta t over n squared. 3 points, delta t over n cubed. So this is wrong at lower orders. So we'll go through and we'll do the analysis with this for now. And we'll fix this, but this is subtly wrong. So let's see what we would get. So this would equal n minus 1. Over here we would get a delta t over n. And we get a 1 minus t plus delta t over n to the n minus 2. Now let's take the limit as n goes to infinity. As n goes to infinity, what does this expression here look like? It looks like e. Now, does this extra minus 2 matter? I would get a 1 minus crap over n to the negative 2. T is going to be small relative to n. So the minus 2 doesn't really matter. So in the limit, the n minus 1 over n becomes just 1. We have a delta t, so we get e to the negative t plus delta t, delta t. Okay? So this is the probability. Now, as we send delta t to 0, what do we get? So as we send delta t to 0, what do we get? We get 0. So what we need to do is, this is the probability of being in the interval. If we want to find the probability density, we should really be dividing this by delta t. So this is the probability that we're in this interval. This should be approximately equal to t plus, let me do it this way, f of u du, and I'll put a subscript here, I'm sorry, delta t. So we're integrating from 0 to delta t of our limiting density. And this should be approximately equal to f of t. Oh, I'm sorry, I'm going from t to t plus delta t. Sorry. This should be approximately f of t delta t. So if I want to try to sniff out the probability density, this should be approximately the probability density times delta t. So what do you think the probability density is converging to? So as delta t goes to 0, yeah. So as delta t goes to 0, probability density converges to e to the negative t. And again, as delta t goes to 0, does your probability density vary that much in an interval of size delta t? No, right? Your probability density is nice, it's continuous. If the interval is extremely small, there's basically no movement. And so because there's no movement, the value of the integral is just the value at the left endpoint times the length of the interval. And so f of t delta t should be approximately equal to this. So in the limit as delta t goes to 0, this is the probability density. So this is telling you that there's a really nice limit, that the gaps between spacings becomes exponential. How could you verify this? So I'm giving you a theoretical claim. How would you check to see if this claim is reasonable? What should you do? Simulate, right? So really good homework problem. Choose 1,000, choose 1,000,000 data points. Choose them uniformly in 0, 1. Sort them. If you're sorting them, maybe you don't want to do 1,000,000 data points, depending on how good your coding is. Choose at least 1,000. Sort them. And then look at the gaps between the normalized spacings. And see, does it look exponential? Do a histogram. Do a comparison. So that's a really good check to see if the theory is correct. Now, unfortunately, we know that this calculation is wrong. So we know that we've made a mistake. What we're going to do is we're going to get around this by using the cumulative distribution function method. So for those of you who haven't done much probability, this is a wonderful technique. And what I'll do is I'll highlight the main idea. So we have probability density functions f, and we have cumulative distribution functions, which are their integrals. And the densities are non-negative. They integrate to 1. F of x, and I'm going to put a subscript x for my random variable, is the probability that my random variable is less than or equal to little x. So this is the same as the integral from minus infinity to x of my density at t dt. So it's the probability I take on a value at most x. And now I want to know what's the probability I take on a value between t over n and t plus delta t over n. So the probability the gap is in t over n, t plus delta t over n. If I calculate the probability that the first gap is at most t plus delta t over n, and I subtract the probability that it's most t over n, then I'm left with the probability that it's in between. So this is just equal to probability the gap is less than or equal to t plus delta t over n minus the probability that the gap is less than or equal to t over n. Can I now have multiple events between t over n and t plus delta t over n? So before, the old method did not allow us to have, for instance, 3 or 4 events in here. But now, could I have multiple events in here? So this should be in the sections you've read. So can we have multiple events now in the interval? So what does this mean if I have something here? It means I have an event somewhere between 0 and t plus delta t over n. It doesn't say I only have one. It says I have at least one thing. This says I have at least one thing between 0 and t over n. So what's the difference in these probabilities? So if the first gap is over here, is it counted in both of them? Is it counted in the probability of a gap of at most t plus delta t over n? Yes. Is it counted in the probability of a gap of at most t over n? Yes. So if my first gap is in here, it's counted by both. Now assume my first gap is anywhere in here. It's counted by the first, but not by the second. Imagine my first gap is in here now. It's counted by neither. So that difference will give us the probability that the first gap is in here. And it says nothing about the subsequent events. All the other ones could still be in here. That's fine. So this is the advantage of the cumulative distribution function. It's going to be an almost identical calculation, but it'll be accurate and rigorous. Right? So we need to calculate these cumulative distribution functions. So what is the probability of a gap of at most, let's do u over n. And then we'll just take u to be t and t plus delta t. So how should we calculate the probability of a gap of at most u? So there's a couple of ways you can do this. Somebody give me one way you can do it. It may not be a good way, but give me a way we could try to do it.
Why isn't this just the cumulative distribution function?
I'm sorry?
The gap at most over n, you just asking for the cumulative distribution function.
Right, but we don't know what that is yet, right? The argument we did before gave us a CDF, it gave us a PDF of the exponential, but it's not rigorous. It's wrong only in lower order terms, but it's wrong. We could do, oh God, like an inclusion, exclusion, maybe adding a lot more. What if there's exactly 2 things in here, exactly 3 things in here, and exactly 4? But we don't want to do that. How would you calculate the probability that you have your first gap is at most u over n? What would that mean? So you have to have at least one event in here. What's the best way to calculate the probability of at least? And so I'll look at this half of the room. So I'll look at you two guys, because you've taken probability with me. Chebyshev is going to give you estimates. I want to calculate probability. What's the easiest way to calculate the probability that something happens at least once? 1 minus the probability it doesn't happen. So this is equal to 1 minus the probability no gap at most u over n. Right? That's much better. Because if we're trying to calculate the probability that there's at least one gap, oh Lord, we could have 1 in here, 2 in here, 3 in here, 4 in here. It's very painful. Once we choose something in here, other ones could be in here or not. And so the probability of where they are is going to be a function of where that first one is chosen. So there's a lot of nice probability techniques in here. It's using the cumulative distribution function method, and using the at least one is equivalent to 1 minus it doesn't happen. All right, so what's the probability that there are no gaps at most u over n? So if I choose an event what's the probability that it's not within between 0 and u over n? Well, so I want to say I don't want to be in here. Right, so what's this length? It's going to be 1 minus u over n. And how many choices do I have? None? Yes, n minus 1. And so if I take the limit as n goes to infinity, we get 1 minus e to the negative u. Right? So now for us, we want the probability of a gap less than or equal to t plus delta t over n minus the probability that the gap is at most t over n. So that's going to become 1 minus e to the negative t plus delta t minus 1 minus e to the negative t. And now we just have to do some algebra. The ones cancel. And so let's see. We're close enough to the end that I think I can now erase this. Now it's just algebra. So we get negative negative is a positive. We get e to the minus t minus e to the negative t plus delta t. All right. How should we do the algebra here? We're going to end up letting delta t go to 0. Yeah, exactly. So you factor out e to the negative t, and you're left with 1 minus e to the negative delta t. All right, how should we view 1 minus e to the negative delta t? It's approaching 1? It's approaching 0. But how is it approaching 0? I care about how it's approaching 0 with respect to what quantity. N is gone. We've lost big N. It's no longer here. I care about how it gets to 0 with respect to what quantity. What's the only quantity that's left? Not t. Delta t. T is fixed. Delta t is that small window. Does this look like anything to you? Well, but we're nowhere near pi, or we're nowhere near pi I. So there's a couple of ways you can look at this. So this is the part that becomes challenging. How do you look at the algebra? How should you view 1 minus e to the negative delta t? When you see the exponential, what should you do?
Run away screaming.
No, it's only worse if you run away. One of the few times you can't take a log.
How would mean value theorem?
You could use the mean value theorem. That would work. So what's the mean value theorem in some sense equivalent to? The mean value theorem is the poor man's, not central limit theorem. How do you understand what an exponential is? Possibly a really bad question to ask.
I don't. I've sort of baked it until this point.
Sines and cosines. No, that's only if you're imagining. Everything's real here. How do you make sense of
Taylor
an
series.
Taylor series, right? The series
Yeah.
expansion for the exponential.
Or actually,
E to the minus t is 1 minus, now let's do the expansion of e to the minus t. It's going to be 1 minus delta t plus delta t squared over 2 factorial. No, it's not that bad.
I guess.
And now if you look at what happens, you'll get e to the negative t, the ones cancel, and you'll have delta t, and you'll have a minus delta t squared over 2 factorial. And remember what we did before is we divided by delta t. So if I pull out the delta t, I have e to the minus t delta t, 1 minus delta t over 2 factorial. All this stuff will go to 0 as I send delta t to 0 after I've divided by delta t. And so we recover exactly the same thing we had as before. So that's one way you can see what the answer should be. And again, the reason I want to go slowly through this is it's not a goal to see how rapidly we can cover results. It's to get you to the point where you can see how to do these algebraic manipulations, what you should start. Some of you have made some really nice comments today on how to approach things. Please make sure you email me so that when I'm writing letters of recommendation, I can remember to include those. The challenge is, what's the best way to see what's going on? How should I view 1 minus e to the negative delta t? Another way to view this is the same 1 minus e to the negative delta t. I can write that as negative 1 times e to the negative delta t minus 1. Does that expression in the brackets look like anything, or the start of anything? How could I rewrite the 1? I've got an e to the negative delta t here. How might I want to write the 1? Write it as e to the negative.
Like, are you saying just like, do you get a
Okay, so if I'm going to put a delta t down below, what do I have to put upstairs? Okay, so now that's okay because I've now multiplied by 1. I've got this as e to the negative. Would it help if I write it as 0 plus delta t? What should I subtract off? It's looking a lot like a derivative. I do like derivatives. What should I subtract off? It's got to equal 1. How should I write 1? I'm writing the first one as e to the negative 0 plus delta t minus something over delta t. This should be what? E to the negative 0. If I write it like this and I take the limit, this is just the derivative of e to the negative x. What's the derivative of e to the negative x at x equals 0? It's just negative 1. And this is the delta t that we needed from before. So when we put everything together, we get e to the negative t delta t 1 minus e to the negative delta t. Let's divide this by delta t, because that's what we were doing before to calculate the density. Sorry, we don't have the delta t yet. This was the expression we had. We divide by delta t, and we take the limit as delta t goes to 0. So this is then going to be the limit as delta t goes to 0 of e to the negative 0 plus delta t minus e to the negative 0 over delta t times negative e to the negative t. And this limit is just negative 1, so we just get e to the negative t. So we recover what we did before. And this is why the suggestion of using the mean value theorem actually does work. Right? If I want to look at this difference, I can view this as the exponential function at 0 minus the exponential function at negative delta t. So it equaled the derivative of the e to the negative x at some intermediate point times delta t, the length I've traveled. And then you take the limit as delta t goes to 0. So you can make all of these work. They're all very similar calculations. And when the dust settles, we've now shown that the spacings between adjacent events is exponential. What was the only thing we assumed about the points x1 through xn? They're independent. So then the question becomes, how much of this argument depends on them being independent, and how much of it depends on that other thing we assumed which was not mentioned? And they're uniform, right? So we made two assumptions. We made the assumption that they were independent and they were uniform. Do you think dropping independence will change the spacings? Or do you think dropping independence could change the spacings? What do you think? I'll ask this side of the room because you seem a little bit quieter. Thoughts? Give me an extreme situation where they're all dependent. And show me how that will affect the spacings. If they're all the same, right? If they're all the same, they're highly dependent, and the spacing distribution is going to be very different. So if I drop the assumption that the points are chosen independently, I expect wildly different behavior, or at least the potential for wildly different behavior. Dropping uniform, that's much more interesting. What would happen if we dropped uniform? So we'll still assume that they're independent. So we've got 5 minutes left. Let's just try to set up the calculation now. Now the first problem is if we drop the assumption that they are uniform, do all points behave the same, or do some points behave differently? Could behave very differently. So the very beginning of our calculation now is no longer available. We were able to assume, oh yeah, just choose any point as the starting point. Well, it now depends. And so you might have to say, well, what's the probability I observe a point here? And given that I've observed a point here, what would the distribution be? So you can definitely talk about the distribution from a certain point, but that will then be weighted by how likely it is to get that point. There's a beautiful subset of probability that's called ordered statistics, where you have a bunch of random variables, and you look at, can you write down formulas for the different random variables when you order them? So for instance, you have, x1, x2, ... xn, you then have y1, y2, yn, where you talk about them being ordered. And there are explicit densities. It would take us, a little bit far afield to write down the explicit densities for the y's. But you can actually explore numerically what would happen if you change the density from uniform. Maybe take any nice continuous density on 0, 1 and see what that does. And if you have enough points, maybe you will still see locally that things are exponentially distributed. And you might then conjecture that this might hold for a large class of smooth distributions. So if you have finished all your reading and are bored and are looking for additional things to do, try doing some numerics. Try looking at some other densities and see what comes out. And then make a conjecture. Now, what is the fundamental lie from Calc 2? Or the fundamental deception we try to do to all calculus students? We try to convince them of something that's false. So when you leave Calc 2, you often feel like you know how to integrate functions. And the reason is because as professors, we spend a lot of time giving you functions that have nice antiderivatives to make you believe that you're learning something. You are learning something in Calc 2. But most functions don't have clean forms for the antiderivatives. When you're choosing your densities, are you choosing nice standard densities that have really good PDFs? If so, is that a good enough model for the real world? Or for a general distribution, are you not going to have something so nice? What could we use to try to approximate a nice continuous density? How could we write that? How could we approximate a nice continuous function? Yeah, with the Fourier series, right? So maybe all that Fourier stuff we did could be useful. Maybe we could look at densities that are finite linear combinations of sines and cosines and try to get some, results from something like that. And any nice continuous density can be uniformly approximated by its Fourier series. We don't have to worry about differentiability, just continuity is sufficient. So there's a lot of stuff you can do to try to push this further. So by now you've had a couple of days to do the reading, but just in case, please make sure you've reviewed chapter 15 on random matrix theory, because we're going to start doing that in earnest on Wednesday. And we're going to start trying to apply the techniques we've just done here to understand the spacings between eigenvalues of matrices. And the question might be, who cares about the spacings between eigenvalues of matrices? It turns out that these eigenvalues model an incredible wealth of phenomena, from energy levels of heavy nuclei, to zeros of the Riemann zeta function, to when buses choose to stop in Cuernavaca, Mexico. They've applied this to so many things. It's another universality law. Whenever you have universality laws, this is nice. Oh yeah, the limiting behavior, I understand what that's going to be. This is one of the reasons the central limit theorem is so powerful. It applies in so many different situations. All right. This is a close enough place to stop, given that I am still on medication, so we will continue on Wednesday.